Hello everyone, welcome to the KV Physics Academy. Today we are going to the start of statistical mechanics. Okay, now we know that in statistical mechanics some cases are relativistic case, some one are non-relativistic case. We know that what is the energy relation between a relativistic case and a non-relativistic case. Relativistic case E is equal to PC. Non-relativistic case E is equal to P square upon 2m. Yes or no? This is the kinetic energy of relativistic and non-relativistic case. Okay. Now we know that. Now here problem they ask the equation of a state of an ideal gas in a non-relativistic case. Non-relativistic energy E is equal to P square upon 2m. P square upon 2m. Okay. Means here power of P is 2 or power of K. Now we know that P is equal to H cross K. H cross K. Then P square can be written as H cross square K square upon 2m. H cross square K square upon 2m. Once you memorize this trick, then you getting this answer in just a second. See here, come to the point. Now non-relativistic case, energy is equal to this one. Now here power of K is directly proportional to E to the power directly proportional to K to the power m. Okay. Now our tricks is this one. E directly proportional to K to the power s. K to the power s. Energy directly proportional to K to the power s. Then we can apply this trick. Here, this part is a common for all the dimension, all the power of s, all the power of K. PV is equal to okay S upon D U. S upon D into U. Okay. S means power of K. S means power of K. D means dimension. D means dimension. Okay. Here is a nothing is mentioned. Nothing is mentioned for dimension. Nothing is mentioned for dimension. Then we can take this is a 3D case. This is 3D case. Nothing is mentioned. Dimension 3. Dimension 3. Okay. And we can take 1D, 2D or 3D. Any case E is equal to H cross square K square upon 2m. Got it? Means here energy will be same for 1D case, 2D case, 3D case. Okay. Relation between E and K will be same for 1D, 2D, 3D. What is the S here? Now comparing with this one, then S is equal to 2. We getting S and D value, just substitute here. Then we getting PV is equal to S2 upon 3U. This is the relation between PV is equal to 2 upon 3U. 2 upon 3U. This is for 3D case. This is for 3D case. This is apply for all the cases. How? See here. We can take non-relativistic case, initial one. Non-relativistic energy is equal to H cross square K square upon 2m. Means E is directly proportional to K to the power 2. Means here S is equal to 2. Okay. Now we can find out for 1D. Means D is equal to 1. D is equal to 1. S is equal to 2. Okay. Means here PV is equal to dimension 1. Power 2. Means 2 U upon 1. Means or PV is equal to simply 2U. Simply 2U. Or this can be written as P is equal to yes 2U upon V. 2U upon V. For 2D case, 2 dimension, D is equal to dimension. D is equal to how much? 2. S is equal to 2. Then PV is equal to or PV is equal to yes dimension 2. S also 2 upon U. Means P is equal to how much? U upon V. U upon V. This is for 2D case. And now we can find out for 1D case. Third one, 1D case. 3 dimension. Sorry. 1D, 2D. Next is 3D. 3 dimension. D is equal to 3. S is equal to 2. Then PV is equal to 2 by 3 U or P is equal to 2 by 3 of U upon V. This is for relativistic case. This is for non-relativistic case. This is for non-relativistic case. Non-relativistic case 1D 2U 1D 2U 2D U upon V 3D 2 by 3 U. Okay. And same trick apply for non-relativistic case. This one for relativistic case. A relativistic. Okay. For relativistics, we know that E is equal to PC. Okay, E is equal to how much? PC. And this can be written as H cross KC. H cross KC means E is directly proportional to K. Is directly proportional to K. Means E is directly proportional to K to the power S. Comparing here, S is equal to 1. S is equal to 1. PV is equal to S upon D. U. Yes, for 1D, 2D, 3D, 1. Okay. 1D. PV is equal to S. S is equal to how much? 1. D is equal to 1. Okay. Next, for 2D, PV is equal to 2D case, S value 1. 2D, 2. For 3D, ES 1. Generally, they ask for 3D case, 2 by 3U, and 1 by 3U. This is for relativistic case. This is for relativistic case. This is for non-relativistic case. Always memorize. And what is the next question? Is that they don't give the dimension generally. They don't give any dimension directly. By default take the 3 dimension. Otherwise, whatever the given dimension is a 1D, 2D or 3D, then we can find out the particular case. Okay, at that time don't take directly 2 by 3 or 1 by 3. Next problem, Feb 2013. Two identical particles are to be distributed over 3 energy levels, treating the particle as a distinguishable Maxwell-Boltzmann particle. The number of ways in which particle and the number of ways in which particle can be distributed. The number of ways in which particle can be distributed. Okay, number of ways in which particle can be distributed. Now see here. Number of ways this particle can be see here, system. Initial one, they are identical particles. Means we can say this one is boson or fermions. Yes or no? Because nature is identical. Identical means they do not distinguish to each other. Yes or no? Then confused. This particle is boson or fermions, but again they are given MB statistics. How to apply this one? Okay, but again they are considered like treating the particle as a distinguishable. Nature. Okay, the distinguishable nature. Yes. Suppose we consider here is a 3 energy levels. How many energy levels? 3 energy levels. First, second and third. 1, 2, 3. How many particles? 2 particles. Distinguishable, indistinguishable. Indistinguishable or distinguishable? Distinguishable. Means we consider first particle is A, second particle is B. Okay. How many ways we can place? Suppose we can place A is here, B is here. Okay, no problem. Next, A is here, B is here. No problem. Next, here is A, here is a B. No problem. Next, AB. Okay. Next, AB. Okay. Next, AB. Okay. 1, 2, 3, 4, 5, 6. Okay. Any interchange is possible? No. This one is a classical particle. And MB statistic is applicable. For this case, no restriction. We can place 1 particle, 2 particle, or all particles in one state. No problem at all. Okay, means we can place the 2 particle in first state. Yes. Next, we can place a 2 particle in this state. We can place in this particle in this state. Yes. Any other possibilities is there? No. Okay. Only these possibilities are there. That's it. Okay. Measure now. 1, 2, 3, 4, 5, 6, 7, 8, 9. Means here maximal distribution. How much? 9. Here important thing is that this particular distinguishable and MB statistic is applicable. How much distribution? Gi raised to Ni. Gi raised to Ni. Gi raised to Ni. Okay, means number of ways. W is equal to Gi raised to Ni. Gi means number of cells. Gi means number of cells. Number of cells. Okay, and Ni means number of particles. Number of particles. Okay, how many particles are given here? 2 particles. And energy levels 3. 3 to the power 2 means how much? 9. Got it. Next. Let E be the E bar be the mean kinetic energy, and V is the volume of the classical ideal gas. Classical ideal gas. The pressure of the gas is numerically equal to. Now, system is classical. Yes or no? And non-relativistic. This one is a non-relativistic. Yes or no? Non-relativistic. E is equal to P square upon 2m means H cross square K square upon 2m. Yes or no? H cross square K square upon 2m. K value 2. Nothing is mentioned by default. By default, this one is a 3D case. 3D case. D is equal to 3. S is equal to 2. Then D upon S. S upon D. E upon V. So the option is correct. Option number 1 is correct. Okay. So many exams this question is asked. Next question. The equation of state and ideal gas in extreme relativistic case. Extreme relativistic case. Approximation is given by. Okay. Now here system is a relativistic. Then energy is equal to PC, and we know that H cross Kc. H cross Kc means here energy directly proportional to K to the power 1. K to the power 1 means E is directly proportional to K to the power 1. And we know that we can apply the trick. K to the power S. Means what is the value of S? S is equal to 1. Nothing is mentioned. Nothing is mentioned by default. This one is a 3D case. 3D case 1 by 3. 3D case 1 by 3. This is a very simple question. Okay. But always memorize this trick. Dimension and power of K. Power of K. Next. Consider distributing two identical particles over their energy or 3 energy levels. 2 particles, 3 energy levels, distributing energy levels, treating the particle as a indistinguishable. Fermi-Dirac, indistinguishable and Fermi-Dirac. Fermi-Dirac. How many particles? 2 particles. How many energy levels? 3 energy levels. Okay. Now this particle are distinguishable, indistinguishable. This particle are indistinguishable. Means we consider A particle. First particle is A, second particle is A. Okay. In a statistical mechanics, maximum we can place 1 particle in 1 state in FD statistic. Always memorize. For FD, maximum 1. Minimum, we can place 0, no problem at all. But maximum is 1 for statistical. In quantum, we can place 2 particles, no problem. But class SM, always maximum is 1. Okay. Means we can place first particle here, first particle here, second particle is here. Next, A, next, A. Don't take replace A, or we can place here is a 2A, here is a 2A, 2A. No, this one is not allowed in SM. SM max 1 particle. Maximum 1 particle. Means here answer is 963 to the power 3. Which of the following option is correct? Only 3 possibilities will be there. Then option number C is correct. Option number C is correct. What it in SM never exceed 1 number. Quantum we can place 2 electrons in 1 state, no problem. But here is maximum, we can place 1 particle. Next question. What is this one? The energy density of a function, the energy density of photon gas maintained at a temperature T. Energy density of photon gas maintained at a temperature T is proportional to T to the power. Here they ask density, energy density. Energy density is directly proportional to T to the power 4. T to the power 4. Okay, and number of photon is directly proportional to T to the power 3. T to the power 3 means energy density per unit volume is directly proportional to T to the power 4 for BBR. Okay, or photon gas. This is equal to how much? This one. Means which option is correct? Option number D is correct. Okay, got it? T to the power 4. T to the power 4 means N is equal to 4. Next, in a canonical ensemble, the system is maintained at a fixed temperature. The canonical ensemble, the system, option number 1, is maintained at a fixed temperature. Can exchange with the surrounding. Can energy is exchanged with the surrounding. Can exchange energy with the surrounding. Okay, can exchange the number of particles with the surrounding. Next, completely isolated from the surrounding. Okay, there are 3 types of this ensemble. First one, canonical, microcanonical, canonical, and grand canonical. Okay, or we can take grand canonical, canonical, and the microcanonical. Grand canonical, microcanonical. Okay, here grand canonical, both are changing. Or we can take the example here. Grand canonical means open system. Okay, grand canonical example is a open system. Okay, open system means we can take a cup of tea. This one is open system. Okay, means here number of particle of the tea also change, as well as temperature also change. Yes or no? You don't see properly how much tea will be evaporated. Only see that after some time your tea will be cooled down. Yes or no? But in this case, some amount of vaporization also possible. Okay, means in this case, number of particle as well as energy both are changing. Got it? Means here number of particle and E both are variables. Both are variable. Got it? In which case, NH, grand canonical, both number of particle and energy both are variables. So example, open system. Second one is canonical. Canonical is closed system. It's a closed system. Okay. Suppose closed system means suppose we can take a tea. Suppose we can take the tea in glass and we can place some cover with this glass. Then after some time, what happen? Its temperature is decreases, but the number of particles remain constant. Yes or no? Means in closed system, N is constant, but E changing, is variable or changing. In which canonical? Canonical. And microcanonical is an isolated system. Isolated system means here we can take the example of thermos. In thermos, we can place tea inside the thermos. After 1 hour, tea quantity and temperature both are same. This doesn't change. Okay, means here number of particle N also constant, E also constant. Got it? In which case? In microcanonical. But in canonical, N is constant, but E is a variable. In grand canonical, both are variable. Which option is correct? Is maintained by fixed temperature, not maintained is fixed. Now here, see here. Temperature is changed, then and then only energy will be changed. Yes or no? Means temperature is not fixed. Second one, can exchange the energy with the surrounding? Yes, energy is changing. Can exchange the number of particles with the surrounding? No, because this one is a constant. Okay, and this is completely isolated? No, this is a completely isolated. System is microcanonical. System. Next question. December 2013, third paper. Okay, consider system of non-interacting atoms, each having an orbital angular momentum Z is equal to 2. A constant magnetic field H is applied along the Z axis. The total number of microstate of the system. Okay. Now here once again n number of particles. They are given n number of particles. First one, non-interacting atoms, each having the orbital angular momentum orbital angular momentum J is equal to how much? 2. J is equal to 2. Okay, applied along Z direction. Now here they are given J is equal to, means how to find out the basis here? Basis is equal to 2J plus 1. J is there, then 2J plus 1. S is here, 2S plus 1. Yes or no? S is equal to how much? S is equal to, S is given, then base is equal to 2S plus 1. Here, J is given, 2J plus 1. Got it? Now, here, what is the value of J? J is equal to 2. Then basis is equal to, yes, 2 into J is equal to 2 plus 1. Okay? Means basis is equal to how much? 5. Basis is equal to 5. And how to find out the number of microstate? What is the relation between microstate and a basis? Is equal to basis raised to n. Okay, what is the basis here? 5. So 5 raised to n. 5 raised to n means this basis does not change for first particle, second particle, third particle up to n. All particle basis will be same. Suppose for one particle basis is, suppose, like consider at -2, -1, 0, 1, 2. Okay, means this basis is for all n particles. All n particle will be same. Got it? This is the all value same for n particles. Hence, omega, number of microstate, is equal to how much? Basis raised to n. Suppose they ask what is the entropy, then S is equal to how much? K ln omega, then K ln 5 raised to n, means this can be written as nk ln 5. Which option is correct? 5 raised to n. This one is correct for number of microstate. Only basis 5. And here they ask, but number of microstate, hence 5 raised to n. Next question. December 2013, third papers. Okay, two identical indistinguishable particle are to be distributed for 3 energy levels or state. The number of ways of distribution for fermion gas and boson gas respectively will be. Means here which component is important? Fermi gas and Bose gas. First one. And second one, two identical particles. How many particles? Two particles. How many states? 3 energy state. Okay, this one is the important ones. Two particles, 3 state. For B and FD. For B and FD. Okay. Now, system distinguishable, indistinguishable. As both particles will be same. AA. Okay. Now, first one we consider they are given Fermi. Maximum 1 means AA. First one. Second one AA. Third one AA. Any other possibilities? No. Because here we can place maximum is 1. Means option number 3. In how many cases option number 3 is correct? 1, 2, 3 option. 3 आहे बरोबर आहे. पण here first they ask fermions. Means 3 in only C option. But check B is also for boson. Boson also identical particles. Okay. Means AA first, AA second, AA third, next AA, next AA, next A. Got it? Means here maximum ways 6 ways. Boson 6 ways. Yes or no? Boson is 6 ways. And fermions 3 ways. Always memorize this question. This is a very important. Which option is correct? 3 and 6. 3 for B. First they ask fermions, hence first write on the 3, and the second boson, hence write on the 6. So we can interchange 6, 3 also. Correct answer there. Okay. Means in this case, option number C is correct. Next question. What is the next question? The critical temperature Tc for Bose-Einstein condensation depends on density N of the gas as. Okay, density and temperature relation. We know that TB formula, Bose temperature is equal to how much? 2 pi S cross upon mk inside the bracket n upon 2.162 bracket is to 3 by 2. Means here, what is the relation between n and TB? TB is directly proportional to, here divided by volume, then TB is directly proportional to n to the power 2 by 3. N is a density. Okay, means TB is directly proportional to 2 to the power n to the power 2 by 3. Means option number B is correct. Why? Because this formula is this one. Okay. Next, well, how to memorize this one? Fermi energy and this one same relation. Fermi energy and temperature. Fermi energy also. Here remaining all are constant. Remaining all are constant. Means F is directly proportional to n upon V bracket is to 2 by 3. N upon V is nothing but small n. Small n to the power 2 by 3. Yes or no? Means Fermi is directly proportional to n to the power 2 by 3 density, and Bose temperature also directly proportional to n to the power 2 by 3. Means we have to some idea for memorizing these two formulas. Okay. Fermi is directly proportional to, suppose k n to the power 2 by 3. Next, our aim to find out the wave vector. Now we know that E is equal to P square upon 2m. Okay. This one is a Fermi, write down Pf. Means this is equal to how much? Pf square is equal to k n to the power 2 by 3. Means Pf is directly proportional to n to the power 1 by 3. Yes or no? Means Pf is equal to some constant, A into n to the power 1 by 3. Okay, but our aim to find out the k, not find out the p. Then what is the relation between p and the k? We know that Pf is equal to h cross kf. H cross kf is equal to A n to the power 1 by 3. Means simply kf is directly proportional to n to the power 1 by 3. Always memorize this relation. E is directly proportional to n to the power 2 by 3 Fermi gas. P is directly proportional to n to the power 1 by 3 for Fermi gas. Kp is directly proportional to n to the power 1 by 3 gas. Okay, next, temperature. Tf is directly proportional to n to the power 2 by 3. Always memorize. We know that E is equal to how much? Kt. Ktf. Okay. Hence, Tf is directly proportional to n to the power 2 by 3. Velocity. Vf is directly proportional to n to the power 1 by 3. Okay, said exam they ask any one of the relation for Fermi gas.